Welcome to the deep dive. Today, we're plunging into, well, a really fascinating topic where AI and robotics meet.
It's an exciting space right now.
Absolutely. And for years, the phrase run it on the robot, it was almost a punchline in robotic circles.
Yeah, you heard that a lot, usually followed by a sigh.
Right. We saw perception pipelines just eating up bandwidth, planning codes slamming into GPU limits, and the smallest Wi-Fi glitch could just freeze up a super expensive robotic arm. It felt like constant fighting against limitations.
Definitely.
But then Google's Gemini team came along with Gemini Robotics On-Device, and they seem to have just completely flipped that script.
They really have. It's a significant shift.
So today we're going to unpack exactly how this tech works, and maybe more importantly, why it matters to you listening in. Help you get up to speed fast.
That's right. This technology, it really tackles some long-standing roadblocks in robotics. It's moving these ambitious ideas from that maybe someday pile right into, we can do this today.
So at its heart, what is it?
At its core, Gemini Robotics On-Device is basically a full-brain vision-language action that actually lives on the robot itself.
Okay.
Which cuts out that constant need for a connection back to the cloud.
You mentioned that punchline era. Let's dig into that. Those specific frustrations, the bandwidth, the GPUs, the Wi-Fi. How did those technical limits actually, hobble robots in the real world? What problems did companies face?
Okay, well, it really all boils down to something robotics teams are obsessed with. It's often triple underlined in their diagrams.
Yeah.
The latency budget.
Latency budget, right. The time delay.
Exactly. That tiny window of time you have for data to travel, get processed, and for the robot to react. And it's tight.
So what happens when it's not met?
Well, think about it.
Yeah.
Even small vision delays. They break grasp alignment. The robot misses.
Okay.
Language delays mess up that crucial human-robot timing, maybe in a collaborative task.
I see.
And network delays.
Yeah.
Well, they can just break everything all at once.
Yeah.
I actually saw a demo once where this expensive arm just froze, completely stopped, because someone started microwaving popcorn down the hall. Interference.
No way.
It sounds silly, but that's the kind of infuriating real-world problem we're talking about.
So not just theory.
Not at all.
Yeah.
Imagine warehouse bots just sitting there waiting for a cloud round trip before grabbing the next item.
Okay, yeah. Slows everything down.
Or surgical assistants losing track of tissue because the operating room Wi-Fi decided to hiccup. Even space missions.
Yeah.
Rovers on Mars were using up precious deep space network time just for simple commands.
Wow.
So it really raises this critical question. What happens when that connection is just gone? Operations grind to a halt. Lost productivity, lost money.
That really paints a picture. Okay, so that's the problem. What exactly is Gemini Robotics On-Device that solves this? What's the core innovation that lets them put the genius right where the action is?
Well, fundamentally, it's a compact version, a sibling, of Google DeepMind's main Gemini robotics model that came out in March. They share this multimodal backbone. You can think of it like the robot's central nervous system. It merges everything, images, language commands, low-level control signals all at once.
All integrated.
Exactly. But the key architectural difference with this on-device version is clever. It keeps the really heavy, complex perception and reasoning stuff in the cloud. But it ships a lightweight action decoder that runs locally, right on the robot.
An action decoder, what does that do?
It's kind of like an autopilot. Constantly predicts the next few moves based on the cloud's overall plan. This means it keeps things running smoothly, even if that main brain connection flickers.
Ah, okay. It smooths things out.
Precisely.
Yeah.
And there's this clever rolling horizon trick they use. The local decoder predicts several short motion chunks at once. These overlap in time.
Right.
And that effectively hides the, say, 160 millisecond delay to the cloud behind a much faster, like 50 hertz local control loop.
So the robot feels more responsive.
Much more. The end result is a closed-loop latency of about 1/4 of a second, which sounds like maybe a lot, but in robotics, that's actually good enough for really tight, graceful two-arm manipulation.
Impressive.
And this whole release is defined by what they call 3 pillars. First is dexterity. We're talking single-millimeter precision. Things like zipping lunch bags, folding shirts, even threading zip ties.
Wow. Okay. Delicate stuff.
Very. Second is adaptability. It allows for really rapid fine-tuning. You can teach it a new variation of a task with as few as, say, 50 demonstrations.
50? That's not many.
No, it's incredibly efficient.
Oh.
And the third pillar is offline resilience, which just means the inference, the thinking survives even with, quote, 0 bars of signal.
The connection can completely drop and it keeps going.
For a period, yes, executing the locally buffered plan. And crucially, this all runs under a strong safety framework. Semantic safety filters, low-level motion guards, the works.
Okay, connecting those technical bits to the real world. That's where it gets really compelling. You've laid out the tech, but how does this local processing actually solve those latency and dependency nightmares we talked about? It almost sounds, well, too good to be true. Are there trade-offs?
That's a fair point.
Yeah.
Gemini Robotics On-Device attacks the problem from two main angles. First is what they call predictive buffering.
Predictive buffering.
Yeah, that local decoder. It streams several short, like sub-second motion commands that overlap in time with the cloud communication.
Okay.
So the robot isn't just sitting idle, waiting for the next single instruction. It always has a short-term plan it's working on.
It's always a few steps ahead, locally.
Exactly. And second, there's essentially no external dependency for the core reasoning once the model is loaded. The heavy model waits. They stay cached right there on the robot's disk.
So even if the whole factory network goes down?
The robot can potentially finish its current cycle, like a pick-and-place run. It doesn't just freeze instantly. This makes robots less like tools tethered to the cloud and more like self-reliant agents, capable of some independent action.
That's a big shift.
It is, and Google's own benchmarks back this up. They tested the on-device version on tasks. It wasn't explicitly trained on zipper pulls, dealing cards, packing lunch boxes, stuff that used to need a whole rack-mounted workstation.
Right.
It achieves similar success rates running just on the device. It's actually fascinating how much performance gain you get just by moving that one critical part, the action decoding, onto the robot itself.
That is fascinating. But okay, beyond just speed, what about the intelligence itself? How does a robot actually think and learn with this kind of vision language action model? Is it different from older methods? Does that planning mapped in mean it's less flexible for totally new situations?
Well, the traditional way was this sort of brittle chain, right? Images go to a vision model, detections go to a planner, then waypoints go to a controller. Each step adds delay and potential points of failure. Fragile interfaces.
Makes sense.
Gemini Robotics On-Device just collapses that entire chain.
Yeah.
It uses a transformer backbone, similar tech to large language models, that directly takes in raw camera frames and a natural language prompt.
Like just telling her what to do in English.
Exactly. Like pick the green cube and stack it on the blue one. The same network then directly outputs the action chunks.
What kind of actions?
Things like 6 degrees of freedom gripper, poses telling the hand exactly where and how to orient, along with jaw widths for the gripper, and timing cues. So, yes, the planning really is baked in.
And the local part, the action decoder.
Right, that uses the latest understanding from the main model to project maybe second into the future, returning a mini plan, a trajectory. And crucially, if that cloud link does drop, it keeps generating those short, safety-checked moves based on the last good plan it received until the connection comes back or the task gets aborted.
And flexibility for new things.
That's where the foundation model comes in. Its massive pre-training gives it a really broad understanding of general concepts. So while it excels at variations of tasks it knows, it can still make reasonable attempts at novel variations within those learned domains. It's not starting from scratch.
That base knowledge is key. And you mentioned that adaptability pillar learning with just 50 examples. How does that work? How can it learn so fast?
Yeah, that's the fine-tuning workflow. It's pretty streamlined. The standard recipe is just 50 labeled demonstrations.
What does that involve? Collecting data?
Basically, yeah. You'd record stereo images, the robot's joint positions, and package them up with simple natural language descriptions of what's happening.
Okay.
Then you use their command line tool, Flywheel Cli Train. That sends your data to the cloud.
And the cloud does the heavy lifting.
Right. The cloud adds your examples to its huge pre-training data set and distills a tiny, really tiny delta checkpoint. It's just the changes needed for your specific task.
Not a whole new giant model.
Exactly. You flash this small delta file onto the robot, and you're basically done. And the results are impressive. They say those 50 trials can routinely double task success rates.
Why such a big jump from so little data?
It's because the foundation model already understands the abstract concept like zip lunch bag in general. Your 50 examples just help it nail the specifics, the local geometry, the feel of your bag, the quirks of your robot's gripper. It's specialization, not learning from zero.
That makes sense. These technical leaps are really something. Now, let's bring it home. Can you give us some compelling real-world examples? Where is Gemini Robotics On-Device actually making a difference today?
Sure, the source material gives some great ones. First, Boston Fulfillment Center, warehouse bin picking.
Okay, classic robotics tasks.
Right. They replace an older perception PC with Gemini Robotics On-Device running directly on the ARM controller's Jetson Orin. It's a small, powerful AI computer.
And the result?
Pick-to-place cycle time dropped dramatically, from 3.2 seconds down to just 1.8 seconds.
Wow, nearly halved.
Yeah. And pick accuracy went up too, because the gripper could actually resample depth images mid-approach, making small corrections on the fly thanks to the low latency.
Very cool. What else?
Okay, ThinkSpace. An aerospace partner tested the model handling payloads inside a mock-up of a pressurized cabin.
On-orbit servicing, maybe?
Potentially. The key thing was the manipulator arm kept stacking experiment trays even when they deliberately cut the cabin radio link,
Yeah.
simulating a comms blackout.
And it just kept working.
It did, based on his local plan. The engineers apparently loved that confidence factor, knowing the AI wouldn't just stop if it couldn't phone home, especially for robots where phoning home is difficult or impossible.
I can imagine. Any others?
Yes, and this one's maybe a bit surprising. Smart farming. A research greenhouse used the SDK to teach a twin-arm robot to harvest ripe tomatoes.
Delicate work.
Very. And they did it with fewer than 100 human teleoperated examples.
Teaching it by demonstration.
Exactly. Now, this robot tracks the tomato's color, the stem position, even accounts for ambient wind, and it clips the fruit without bruising it, all running on battery power with spotty LTE coverage. But the AI stays sharp because it's local.
From warehouses to orbit to greenhouses, that really shows the versatility. So this sounds unique. How does Gemini Robotics On-Device stack up against other models or approaches people might know? What are its key selling points?
Well, looking at the comparisons provided, there are several key differentiators. The big one, it runs with no network connection required after loading. That's a huge advantage over most cloud-dependent models.
The offline resilience pillar.
Exactly. Second, it uses natural language prompts. Makes interaction much more intuitive.
Just tell it what to do.
In many cases, yes.
Yeah.
Third, that fine-tuning ability needing maybe 100 demos or fewer is very efficient compared to traditional methods needing thousands.
Much faster to deploy new tasks.
Right. Then there's the low control latency, around 250 milliseconds, which we talked about, enabling dexterity. It can also handle deformable objects, things like clothes, bags, maybe even dough.
Things that aren't rigid.
Correct. Which has always been tricky for robots. It supports new robot bodies relatively easily. And right now, access is through an SDK in a trusted tester program.
And what about safety? That's always a big concern with autonomous systems.
Absolutely. And they seem to have built safety in from the ground up. The transformer model itself screens the language prompts for disallowed content.
Like what?
Like it would block a command like hit the emergency stop button twice, which could be unsafe.
Okay, semantic understanding of safety rules.
Yes. Then, lower down, the motion planning layers constantly run checks for collisions using virtual cones and enforced velocity limits.
Physical safety guards.
Right. And there's even something called a semantic watchdog that checks the predicted language tokens. Basically, making sure the robot doesn't hallucinate or misinterpret instructions in potentially harmful ways.
Preventing weird emergent behaviors.
Kind of, yeah. And the whole pipeline was rigorously red-teamed, meaning ethical hackers tried their best to break it against a new benchmark, specifically designed for semantic safety.
That sounds thorough. Now, you mentioned the SDK and the flywheel climb for developers. We don't need a coding tutorial, but just briefly, how might someone interact with this? And then let's zoom out to the bigger picture.
Sure. For developers, the SDK and command line interface seem designed to package everything up. Model serving, simulation tools, evaluation scripts. The aim is to make integrating it easier. But you asked about the bigger picture.
Yeah.
If we connect all these dots, the implications of reliable edge deployment like this are, well, they're truly transformative. This really changes the economics of automation, of labor itself.
How so?
Because robots that can think reliably on their own can now go places where advanced automation just wasn't feasible before. Think dusty barns, flooded basements, tunnel networks, places where getting reliable broadband is just a pipe dream.
Right. Environments that are hostile to networks. Exactly. Or think about hospitals. Local processing means sensitive patient data potentially never has to leave the ward. Big implications for privacy and security.
Huge.
And manufacturing lines can avoid those costly stops, those homing pauses that happen when the factory network has even a tiny glitch. It boosts uptime.
So it's about access, privacy, and reliability.
Yes. The arrival of this kind of tech signals a real shift. Just like, laptops freed computing from the big server rooms. On-device robot intelligence is starting to liberate automation from total dependence on the data center.
That's a powerful analogy.
And you can expect ripple effects from that.
No, right.
Maybe smaller support teams needed, definitely shorter iteration cycles for developing new robot skills, and maybe entirely new business models. Imagine fleets of robots learning a new skill overnight from shared data, then fanning out the next morning to work completely offline.
That's a game changer. It really feels like Gemini Robotics On-Device has kicked away that crutch of needing perfect Wi-Fi and racks of GPUs, yet it's still performing these incredibly complex tasks.
It really has. That mix, natural language, seeing the world accurately, and reacting in fractions of a second, it felt like a moonshot not long ago. And now it's becoming accessible, potentially just an SDK install away. Imagine, telling your robot, hey, pack the lunch bag, zip it shut, but be careful with the grapes, and it just does it.
We're getting closer to that reality. And this decentralization of intelligence, it really opens up huge new competitive advantages and, frankly, new questions.
Questions like,
Well, the edge belongs to whoever wields it first, right?
Yeah.
What new applications or maybe even ethical considerations pop up when intelligence is truly spread out to every autonomous system? What opportunities does this create for you, the listener, to engage with this? What stands out to you as the next big step for robots that truly own their decisions outright?